Look at a handwritten number. Easy, right? You instantly know what it is. Your brain does this effortlessly. But how do we teach a computer to do the same? It's trickier than you might think. Computers don't see images like we do. They see pixels, tiny squares of color. Recognizing patterns in these pixels is the challenge. This is where neural networks come in. Inspired by the human brain, these networks are designed to learn and recognize patterns. They do this by mimicking the interconnected structure of neurons in our brains. But instead of biological cells, neural networks use mathematical functions and calculations. Imagine a network of interconnected nodes organized in layers. Each node is like a tiny neuron, processing information and passing it along to the next layer. This is a simplified view of a neural network. The first layer receives the input, which could be anything from images to text or even sound. In our case, the pixel values of our handwritten digit are fed into the network. Each pixel is a piece of data that the network will analyze. This input layer is connected to a hidden layer. The hidden layer is where the real magic happens, as it processes the input data in complex ways. Think of this hidden layer as a detective looking for clues in the input. It tries to find patterns and relationships that aren't immediately obvious. Finally, the hidden layer is connected to an output layer. This is where the network makes its final decision based on the processed information. This layer gives us the answer, the network's best guess about what digit it sees. It's like the conclusion of the detective's investigation. The magic happens in the connections between these layers. These connections are what allow the network to learn and make predictions. Each connection has a weight, which is a numerical value that determines how strongly one node influences another. These weights are adjusted during the training. A numerical value that determines how strongly one node influences another. The network learns by adjusting these weights to improve its accuracy. These weights are the key to the network's learning. They determine how the input data is transformed as it passes through the network layers. Initially, they're set to random values. This randomness is crucial because it allows the network to start from a neutral point without any biases. As the network sees more and more examples of handwritten digits, it adjusts these weights. This process is known as training, where the network learns from its mistakes and successes. This adjustment is guided by a learning algorithm, a set of rules that tell the network how to change the weights based on its performance. The algorithm evaluates the network's output and makes necessary corrections. The goal is to find the perfect set of weights that allows the network to accurately recognize digits. This is achieved through continuous iterations and refinements. Think of it like finding the right combination on a lock. Each weight adjustment brings the network closer to the optimal solution. Each weight is like a number on the dial, and the network has to keep trying different combinations until it finds the one that unlocks the correct answer. This trial and error process is essential for the network to learn and improve its accuracy over time. Section 4. Hidden layers. Unveiling patterns. The hidden layer plays a crucial role in this process. It's here that the network starts to identify patterns in the input data. Each node in the hidden layer becomes sensitive to specific features. For example, one node might become an expert at recognizing loops, while another might specialize in detecting diagonal lines. By combining the information from these specialized nodes, the network builds a more complex understanding of the input. It's like piecing together a puzzle. Each node contributes a small piece of information, and the network assembles these pieces to form the complete picture. Section 5. Learning and beyond. This process of adjusting weights and identifying patterns is called training. During training, the neural network learns to make sense of the data it is given. It adjusts its internal parameters, known as weights, to minimize errors and improve accuracy. The more data we feed the network, the better it becomes at recognizing handwritten digits. This is because the network has more examples to learn from, allowing it to identify subtle patterns and variations in the data. Once the network is trained, we can unleash it on new, unseen digits, and it will use what it has learned to make predictions. This ability to generalize from training data to new data is what makes neural networks so powerful. The beauty of neural networks lies in their ability to learn from data. As they process more information, they become increasingly accurate and efficient. This continuous learning process is what sets them apart from traditional algorithms. We don't need to explicitly program them with rules for recognizing digits. Instead of hard-coding specific instructions, we allow the network to learn from examples, making it adaptable and flexible. Instead, we simply provide them with examples, and they figure out the rules on their own. This self-learning capability is what makes neural networks so versatile and effective in various applications. This ability to learn from data makes neural networks incredibly powerful tools, applicable to a wide range of problems, from image recognition to language translation and beyond. Their versatility allows them to tackle complex tasks that were once thought to be the exclusive domain of human intelligence. The future of artificial intelligence is being written one connection, one weight at a time. As we continue to develop and refine these networks, we are paving the way for smarter, more capable AI systems that will transform our world in ways we can only begin to imagine.